Okay, in this presentation we are going to look at the gamma distribution. We're going to be looking at arrival rates at a call center. Now you're probably familiar with the Poisson distribution and the exponential distribution, and they're relevant here. In fact, you can sort of consider the exponential distribution a special case of the gamma distribution in this respect. Okay. So arrival rates at a call center, suppose calls come into a call center randomly at a rate of 1 per 30 seconds, 2 per minute in other words, that's an arrival rate. What is the distribution of the time to the second call? Okay, so usually when we're dealing with exponential distributions, it would be the time to the next call. But in this case, the gamma distribution, it doesn't have to be the next call, it can be any number of calls down the line. What is the probability until we get the 10th call? Using this distribution, calculate the probability that the second call arrives within 1 minute. Use approximations if necessary. Now that's going to be important in this case. This is really just a sort of demonstration of the gamma distribution. It is quite complex mathematically. I'll just show you it, but we won't really go into too much detail. But there is an approximation that we can use, and we'll just sort of rely on this. This is sort of pen and paper exercise, essentially. Using the appropriate discrete distribution, calculate the probability that at least 2 calls are received in a minute. Okay. What is the exact distribution of the time to the 200th call? That's just the statement of the distribution. Using the central limit theorem, give the normal distribution, which would approximate the distribution from exercise D. So we're going to be using the normal distribution as well. And use your answer from exercise E. Estimate the probability that the time to make the 200th call is less than 102 minutes. Okay. So just arrive at the arrival rates, how we sort of parameterize that essentially. The rate of calls is 1 per 30 seconds, which is equivalent to 2 calls per minute. Okay. Now, we're going to be looking at the mean and the variance of the gamma distribution. Just as a quick remark, that is alpha divided by lambda, which is the shape parameter and the rate parameter, and the variance is the shape parameter divided by the rate parameter squared. That's going to be sort of coming a little bit later on. Okay, this is more important actually. So this is the cumulative distribution function of the gamma distribution, and we have the rate parameter and shape parameter there, but we're interested in the cumulative distribution function of x, and it's parameterized in terms of alpha and lambda. So we have the incomplete gamma function, lower incomplete gamma function of alpha and lambda times x, and the gamma function of alpha. Okay, that's not pen and paper stuff. That's what you use a computer for. So what we're going to do, next slide, is this approximation. So for our gamma distribution with a shape parameter alpha, if alpha is a positive integer, and rate parameter lambda, we can approximate the cumulative distribution function as follows. We have 1 minus the summation k equal to 0 to alpha minus 1 of lambda k to the power of, or lambda x to the power of k divided by k factorial times the exponential of minus lambda x. Okay, so we're going to use that one. Just actually statement of what we're doing actually. Exercise A actually asks us to make a statement. So just to sort of park the remark about the cumulative distribution function, and actually we'll just go into the questions. Distribution of time to the second call. The time to the second call follows a gamma distribution with a shape parameter k equal to and a rate parameter lambda. So t2, which is the time to the second call, is a gamma random variable with k equal to and lambda equal to 2. Just a statement like that. So moving on to the next part, exercise B, probability that the second call arrives within 1 minute. So using the gamma distribution, we need to find the probability of t2 less than 1 minute. So the cumulative distribution of function is as follows. F of t with parameters alpha and lambda is 1 minus the exponential of minus lambda t times this summation. Now, so we concentrate on this summation for the next part. From k equal to 0 to alpha minus 1. So in this case, alpha minus 1 is 2 minus 1, which is 1. Okay, so we actually have to express the value within that summation. We have to calculate it twice, or express it twice, evaluate it twice, I should say. For k equal to 0 and k equal to 1, and 2t is, for t equal to 2, that is 2 or lambda equal to 2, that is 2t. Okay, getting a bit tongue-tied there. So 2t to the power of 0 divided by 0 factorial is 1. And when k equal to 1, 2t to the power of 1 divided by k factorial, 1 factorial, is 2t. So the evaluation of that summation is 1 plus 2t. And just putting it back into the overall expression, we have f of t with alpha and lambda 2 equals 2 and 2. That is equal to 1 minus the exponential of minus 2t times 1 plus 2t. Okay. So let's evaluate this for t equal to 1. Let's just evaluate it here. So that is 1 minus the exponential of minus 2, 2t being 2 in the case of t equal to 1. And 1 plus 2t becomes 1 plus 2, which is 3. So we end up with 1 minus 3 times the exponential of minus 2. Little bit of calculator work. 1 minus 3 times 0.1353, which is 1 minus 0.4059. And that gives us an answer of 0.5941. So 59.41%. Okay. Now, calculate the probability that at least 2 calls are received in 1 minute. So we're going to park the gamma distribution briefly because we're just going to try and show how this matches up with the Poisson distribution. So if you just read that the question again and forget about the exponential distribution, you'll probably recognize that as the Poisson distribution. So that is Poisson distribution with rate parameter lambda equal to 2 calls per minute. Okay, what we're asked for is probability of x greater than or equal to 2 is 1 minus the probability of x less than 2, and that is 1 minus the probability of x equal to 0 plus probability of x equal to 1. So we're just going to evaluate those out. Probability of x equal to 0 is the exponential of minus 2 times 2 to the power of 0 divided by 0 factorial, which is the exponential of minus 2, which is 0.1353. The exponential of k equal to 1, x equal to 1 is the exponential of minus 2 times 2 to the power of 1 divided by 1 factorial. That is 2 times the exponential of minus 2, and that is 0.2706. So the probability of x being greater than 2 equals 1 minus 0.4059, which is 59.41%. So as expected, this is the same probability as calculated in exercise B. So I won't get into too much detail here, but it is interesting to explore the relationship between the Poisson distribution, the exponential distribution, and the gamma distribution when applied to this context, okay? So they're covering a lot of the same ground, but you might notice that there's subtle differences between the two, particularly in the way the questions are being asked. I won't get into it in too much detail here because I just don't really have the time, but it is worth checking out. Anyway, the exact distribution of time to the 200th call. So we're not asked for any calculations here. We're not going to do any summations from 0 to k equal to, or for alpha equal to 200, or well, k equals 199. That'll be just take us all week. The time to the 200th call follows a gamma distribution with a shape parameter alpha equal to 200 and a rate parameter lambda equal to 2. So T200 is a gamma random variable, alpha equals 200 and lambda equals 2. Okay, that's all we really need for now. So what we're going to do is use an appropriate approximation to model this. And what we're going to do here is approximate the gamma distribution with the normal distribution. We're just mindful of the fact that alpha here is 200, which is large enough, okay? And so using the central limit theorem, the gamma distribution with large alpha, which alpha is 200, that seems reasonable, can be approximated by a normal distribution with the same mean and variance. Here, the mean of T200 is alpha divided by lambda, which is 200 divided by 2, which is 100 minutes. And variance is lambda divided by alpha divided by lambda squared, which is 200 divided by 4, which is 50, okay? And the standard deviation, therefore, is the square root of 50, which is 7.07. So the normal distribution that approximates T200 is normal random variable with mu 100 and variance 50. Okay. So calculate the probability that the 200th call is within less than 102 minutes. So use the normal approximation from exercise E. We need to find the probability T 200 less than 102. So I'm just going to be quick about it here and just use the z-score and the cumulative distribution function of the normal distribution. Z-score is 102 minus 100 divided by square root of 50, 2 divided by 707, and that gives us a z-score of 0.283. So using the standard normal distribution tables, we find this to be approximately 0.6103. Okay, 0.6103, 61.03%. So yeah, so the probability of the mean at the time to the 200th call is less than 102 minutes is approximately 61%. Okay, that's us. A lot of hard work done there. Okay, bye-bye.